Okay, so now we're going to think about an object that gives us a nice region of uniform magnetic field. That object is a solenoid. Now, a solenoid is really just a coil of wire that we send current through. Okay, and now I see we have a question. And Ashwith, can we have class outside? Come on. All right. All right. All right, you asked for it. Here we are in the academic quad of Rice University. We've got our founder, William Marsh Rice, watching over us as we do this lecture. He's actually here in more ways than you know. He's actually buried back there. So perhaps this is not the most respectful physics lecture we've ever had. So what we're going to talk about, though, is creating a uniform magnetic field. So one way to create a uniform magnetic field is just to stand here on the Earth. We are bathed in a uniform magnetic field pointing north. The problem is you can't really change it. You're stuck with this one field, and it's pretty weak, you know, just a Gauss, few Gauss. So we want to think about the device that we use to create a uniform magnetic field, and that is a solenoid. So a solenoid is a cylindrical coil of wire. Cylindrical coil of wire. So if I were to draw a solenoid, it just looks like this. Here's some wire, and it loops around, making kind of a helix. And if you want to make a field, you just send a current through it. Now, a real solenoid that you might use to create a magnetic field is actually one more thing we should add. It's a tightly wound cylindrical coil of wire. So let me draw something a little bit more realistic. We want to get a big field, so we want a lot of current loops, so it looks more like, you know, like this. A lot of loops right on top of each other. It just gets harder to visualize if you go and draw it that way. So in physics, we can't deal with that. In physics, we always deal with models of ideal things. So let's think for a second about how we draw an ideal solenoid. So our model of the solenoid, basically it treats the turns as individual loops. So rather than a helix, it's really just a bunch of rings of current, but current still flows throughout. So just because they're isolated, we still imagine a current I making its way through the solenoid. So now if we think for a second about the magnetic field of a current loop again, here is sort of a current loop cut and shown in cross section. The current might go in here, or I'm sorry, come out here, and it'll go back in here. So it's a full loop. I'm just showing it to you in cross section. If it does that, the current does that, we know the magnetic field in the center will point up. We have calculated the magnetic field in the center of a loop, and it's right there at some value sticking up. If you go off axis, it kind of does this. We've kind of drawn this many times. It kind of goes like that, and it goes like that, and we know everything about the magnetic field is loopy. If you have a current loop, then you get a magnetic field that also makes a loop. And then in the middle, it just sticks up. Okay? So let's think about then how we actually draw then an ideal solenoid. This wasn't an ideal solenoid. This was a single current loop. So let's look at one. Pretty much we just draw circles to represent the cross sections on one side, and then circles to represent the cross section on the other side. And we put something to indicate the direction of the current. So these dots and X's usually mean vectors, but for now we're just talking about the direction of the current. And if it's a detailed drawing, you might even show the backs of the wires, like this. So here is probably, whatever book you're using, draw something like this to represent an ideal solenoid. Or they might leave the wires off. So you're looking at it in cross-section, and you can use the right-hand rule to figure out probably what this field is going to do. Your fingers come out and go in, it's going to make a magnetic field up. So our job now is to figure out what is the magnetic field in and around a solenoid.